All right, so now we're going to talk about Chapter 9, which is the capital asset pricing model. Very theoretical, okay, but it is one of the, it's a contribution that came out of academia. It's not perfect, but it certainly has found its place in the practical world of finance and investing. So let's kind of backtrack here for a moment. And we had talked about in a previous chapter, we said, what if someone had a handful of stocks, maybe 3, 4, 5, 6 stocks, whatever. And we were considering the return that someone could earn on various combinations of those assets and also the risk. And so we could plot each one of those possible combinations. With 5 assets, for instance, there are an infinite number of possible combinations of those 5 assets. Allocating your money, especially if you allowed short selling or margin trading. So let's assume for a moment that this represents those 5 stocks, or rather these dots represent all the possible combinations of those 5 stocks. Well, we're plotting them risk versus return. We're plotting them using standard deviation and also using the return of the portfolio. If you recall, then we were able to find the combinations of all those assets that had the highest rate of return at any given level of risk. From this, if you recall, we were able to identify this portfolio, which was the minimum variance portfolio. And we saw that each one of these portfolios that were represented in blue here were the most efficient. Okay? Really, none of the efficient portfolios are better than another. It depended upon someone's risk tolerance. Well, that was fine until we added a risk-free asset as an alternative. Then we found that when we combine the risk-free asset with all of these different combinations, all of these different portfolios, there did emerge a best portfolio. And it's this portfolio right here in this particular example. Because when we combine the risk-free rate with that portfolio, if you'll notice, we get the best trade-off between risk and return. Because we can obtain a position anywhere on any one of these straight lines, because the return on a portfolio is a weighted average. So we could put all of our money in the risk-free rate or all of our money in any of these portfolios that are efficient or anywhere in between. And so what we found is that the line that connects the risk-free rate and is tangent to all of those efficient portfolios gives us the best trade-off. And so the red portfolio that I've identified is the optimal risky portfolio. You will remember in, I think it was chapter 7, that we actually solved mathematically for that portfolio, because that is the portfolio that maximizes the Sharpe ratio. You remember that? If that's the return of our best portfolio, then the return on our portfolio minus the risk-free rate. Basically, the Sharpe ratio is the slope of that line, and so we are maximizing the excess return divided by risk. That was the Sharpe ratio. So we did that. Okay. Well, that was just 5 assets. All right. And so why don't we assume for a moment that all investors out here, all investors everywhere, have the same information about assets. We all share an identical investable universe. So you don't just have 5 stocks that you could invest in. You can invest in any of the stocks out there. Okay, so I think that's a relatively safe assumption that we all share the same investable universe. Anything that I can invest in, you can invest in, right? So if we all share the same investable universe, then theoretically we could do this exercise again. But instead of using 5 assets, imagine for a moment if we used all of the investable assets. It's the exact same concept, right? If there was an infinite number of possible combinations with 5, well, you know there's an infinite number of combinations with more than 5, especially if we consider that we could use all of the possible risky assets. And if we did that, then we should be able to find any investor who's using the same set of assets, the same investable universe of asset, then everyone should find the same efficient frontier, the same efficient combinations. And if everyone then has the same risk-free rate right here, then everyone should be able to find this same portfolio that is tangent to the efficient frontier, that's tangent to the efficient, the combination of all the efficient assets out there. Now, what I didn't say a moment ago, let's go back to the left when we were looking at just 5 stocks or 4 stocks or 1, this line that we draw is called the CAL, which is called the capital, or stands for the capital allocation line. For this particular investor on the left-hand side who's identified these 5 stocks that he or she wants to invest in, this line represents the best trade-off between return and risk, and so the investor should allocate his or her money somewhere along this line. The investor could put 100% of the money in that portfolio, 100% of the money in the risk-free rate. They could allocate the money anywhere along here by putting some money in the risk-free rate, some money in that optimal portfolio, optimal risky. How do they get up here? Well, that's going to be through leverage, margin trading. Because this arrow that I'm drawing here, that's 100% of your money put in that risky asset. If you're over here, that's 100% of your money put in the risk-free rate. So the only way to have more than 100% of your money invested is to borrow. All right? So that's what we had on the left-hand side. On the right-hand side, what we're saying is if we assume that the entire universe of assets is at our disposal, then we should still be able to come up with the efficient possibilities, the efficient portfolios, all of the portfolios that have risky assets, and that's what all of these dots here represent, combinations of risky assets, and we can find the most efficient of those. Right? So we found all of those on the efficient frontier. We have the risk-free rate that everyone presumably faces the same risk-free rate. We can all go buy a treasury bill. And so if we all have access to the same universe, the same investable universe, all right, then it would stand to reason that we're going to arrive at the same set of portfolios and the same optimal portfolio. This line, when we're looking at this line for all investors, is called the capital market line. So, in this portfolio that we've identified here, which is the most efficient of all of the risky portfolios, all of the risky assets out there, is referred to as the market portfolio. Okay? So it is as your book says, it represents the aggregation, not aggravation, but the aggregation of all the identical risky portfolios. Okay? And since all of the investors out there share the same investable universe, the same risk-free rate, we should be able to find that portfolio. All of us should. And your book goes on to say, it says, since all the investors choose the same risky portfolio, it must be the market portfolio. It's the value-weighted portfolio of all of the assets in the investable universe. Again, I know that this is a lot of theory. It's a lot of concept. All right, now I'm going to go to next page here and draw it again a little bit larger, so we'll have to work with. So I'll put return on this axis, risk on this axis, sigma p, RP. We had our efficient frontier. We've got the risk-free rate. So this line is called the capital market line. We've identified the market portfolio, so this is going to be the standard deviation of the market portfolio. And this is the return of the market portfolio. Okay. So since we have identified, think back to how we got here. We first looked at all of the possible combinations of all the risky assets. Out of all of those risky assets, we found the ones that were most efficient, and we created the efficient frontier. And out of the ones that were the most efficient, we found the most efficient, the mother of all efficient portfolios, and that's portfolio M. So as long as we hold the market portfolio, we are investing in the optimal risky portfolio. Now, not everybody wants the same amount of risk, and so you still have the choice for having more or less risk. If you don't want very much risk at all, invest in a risk-free asset. If you want to hold market risk, invest in the market portfolio. Or you can invest anywhere on this line. It's simply a weighted average, right? And so anywhere on this line is possible. That would be about right here, 50% in a risk-free, 50% in the market. This is probably 75% right here in a risk-free asset, 25% in the market. But as long as we're investing in the market portfolio, then we are facing only market risk. Let me remind you, go up for a moment. I've got a little space here. Let me remind you that total risk, which is measured by standard deviation, equals systematic risk plus unsystematic risk. The systematic influences, we saw that in Chapter 8, plus the unsystematic, which are the firm-specific contributions to the volatility. Okay. Well, if we're investing in the... See, normally, if you look at our what I just wrote, total risk equals systematic plus unsystematic. Normally, if we were using standard deviation as a measure of risk, we would have to recognize that standard deviation is capturing total risk, not just systematic. But since we're in a perfectly well-diversified portfolio, we've invested in the market, there's actually no unsystematic risk. The unsystematic risk has been reduced to zero if we've got a well-diversified portfolio. You probably remember, I think I probably drew this. I hope I did. If not, I'm doing it now. standard deviation of the portfolio, number of securities. And so as we add stocks to our portfolio, we notice that total risk is going down. The total risk is measured by that red line. Total risk is going down. But no matter how many assets we add, we cannot eliminate the market or the systematic risk. What we are able to identify is this risk, which is our unsystematic, our firm-specific risk. So normally when you're using standard deviation as a measure of risk, you have to recognize standard deviation captures both systematic and unsystematic. But if you've got a perfectly well diversified portfolio, let's come over here. It's not totally down to, but it's pretty good. You'll notice that the only risk that remains is the systematic risk, because at this point all of this unsystematic risk, it looks like it's been diversified away. I mean, it's negligible at that point. Okay. So, we see the idea then, if we have a well-diversified portfolio, the only risk that's going to remain is going to be systematic risk. What if I want to, though, practically speaking, what if I'm an investor and I want to invest in Procter & Gamble? How do I determine how much the rate of return that I should expect or require on Procter & Gamble? The idea is, since I'm going to hold a diversified portfolio, the real question is, okay, how much systematic risk does Procter & Gamble contribute to the portfolio? Again, if my objective is to eliminate all the risks except market risk, that means market risk is going to remain. Then when I'm evaluating individual securities, I have to consider not, hey, how much total risk do they have? Because some of their total risk will be diversified away as it's added to the portfolio. What I have to consider is, okay, how much risk is this stock going to add to my portfolio? And the only risk it's going to add is going to be the systematic risk. So I need another measure, really, because what if I told you Procter & Gamble's, let's see, I'll change to green here. Let's say I tell you that Procter & Gamble, oh, that wasn't green after all, was it? Here we go. Standard deviation of Procter & Gamble. Procter & Gamble, right there. So it appears the way I've drawn this is the standard deviation of Procter & Gamble is less than the standard deviation of the market. So do I think then that Procter & Gamble, if that's the standard deviation, that Procter & Gamble is going to plot on this line? And that right there should be the required rate of return on Procter & Gamble. And your answer has to be no, because look, the standard deviation of Procter & Gamble, we know, consists of systematic risk plus unsystematic risk. Right? Standard deviation consists of systematic and unsystematic. And the only risk that's being reflected on our capital market line over here on the left is systematic risk, because remember, all of the portfolios that plot on this blue line are combinations of the risk-free asset and the optimal, most diversified portfolio. So Procter & Gamble's not going to plot on that line. The only thing that plots on that graph is systematic risk. Procter & Gamble's standard deviation also reflects unsystematic risk. So what we need is another measure of risk that really reflects only systematic influences. I'll put return here again. I'm going to put risk here. But we need a measure of risk for individual stocks, for individual portfolios, other than standard deviation. What we need is a measure of risk that's just systematic risk. And we have one. Okay, we have one. You remember our concept of beta. Beta is a measure of non-diversifiable risk. Beta is a measure of non-diversifiable risk. Beta is a measure of how an asset moves relative to the market. You remember, I'm sure, that the beta of the market is equal to 1. So if stock, whoa, that was not a very good beta. If stock J has a beta of 1, then its movement tracks the market. It's just as risky as the market. I'll put same risk as the market. Let's say the beta of stock J is 0.8. Then asset J is less risky than the market. Right. If the beta is greater than 1, then you know that it's going to be asset J's risk is greater than the market risk. Okay. Well, let's approach this the same way we did a moment ago with the CML. We still have our risk-free rate here, and we've been able to already identify the market portfolio. We did that up here. That was the market portfolio. I don't know why I subscripted it P. I'm going to put an M now up here. That should have been an M. Okay. And we know that the beta of the market is 1. So I'm going to find a 1 on my graph right here. And so I know that the return on the market is going to correspond to a beta of 1. The risk-free rate corresponds to a beta of 0. Beta is a measure of risk. If it's free of risk, then its beta is 0. And so I've got this line I can draw. This line looks like that line, doesn't it? That's the CML. This line is called the SML. The SML stands for the security market line, whereas the CML stood for the capital market line. Some of this gets confusing. I should have probably written some of this down. The CAL there stands for the capital allocation line. So when we were looking at, when we combine the risk-free rate with all of those portfolios, let's say of 5 stocks, that the line that we draw is called the allocation line, the capital allocation line. When we consider all of the possible combinations out there of risky assets, the entire market of assets, then the line that we draw is called the capital market line. When we evaluate the returns of a portfolio or a security against systematic risk only, not standard deviation, but systematic risk, that line is called the security market line. Okay. Let's take a look at, it is a line, so let's think about the equation for this line. The equation for this line says, all right, let's put R sub J, because right here, that's the return on an asset. All right. So first, if you remember the equation of a line, you need the y-intercept. So where does this security market line intercept the y-axis? Well, it intercepts it at the risk-free rate. So there's our y-axis. Okay. Then we need our x variable. So we've, what's reflected on the x-axis. On the y-axis, we've got return. On the x-axis, we've got beta. We've got risk. So I'm going to write beta right here. And then you multiply the variable for the x-axis times the slope of that line. The slope. Well, you remember the slope is equal to rise over run. So let's evaluate the slope. All right. let's evaluate the slope of this line. Well, first we need the rise, so we need from here to here, right? That's simply RM minus RF. Sometimes it helps to put some numbers in here, so why don't I do that? I'm going to say, what if the risk-free rate is 3% and the return on the market is 10? Well, the distance then from risk-free to RM is 7, right? So we can take RM, which is 10, minus RF, which is 3, to get us 7. So that would tell us what the rise is. The run is from 0 to 1. From here to here is 1. So we don't even really need to do that, do we? So what we can say is the required return on asset J equals the risk-free rate plus the beta times RM minus RF. This is the equation of that line. And when we write out the equation of this line, it takes on a new form. It's called the capital asset pricing model. So here's the, I don't want to mess up my artwork here, so I'm going to create another slide over here that I'll work from. So my example, I think I said, let's assume this is 10 and this is 4. This is called our SML, our security market line. So, and the equation, as I said, so R sub J equals the risk-free plus the beta times RM minus RF. So let's break this down, this capital asset pricing model formula down. R sub J is the required return on an asset. RF is the risk-free rate. This is what we could get without any risk at all. So if we're looking at, what rate should we require on a certain risky asset, we want to begin with, well, what could we get without any risk? And then we need to add in a risk premium. So this entire term, including the beta through the brackets, is the risk premium that we would require to invest in asset J. Our example here is that the risk-free rate is 4. So if we're going to invest in a risky asset, we want 4 plus something, and that something is something to compensate us for the market risk that asset J has and would contribute to a portfolio. We can break down the risk premium into two parts. We've got beta, which is the systematic risk of security J. Basically, it's a measure of how risky this particular asset is relative to an average asset, relative to the market. And then in the brackets, we have the market risk premium. The market risk premium. All right. So in our example, let's break this down again. If we want to know the required return on asset J, we're going to begin and say, okay, we at least want 4% plus something to compensate us for risk. All right. Now, if this were an average stock of average risk, then we would simply want the return on the market minus the risk-free rate, which is 6. We would be satisfied with a 6% premium. If we're looking at investing in an average stock of average risk, then we would accept the average risk premium. And we would want a 10% rate of return. We would want 4 plus 6, which is equal to 10. Well, let's assume that we're looking for an asset. Procter & Gamble is going to have probably a beta less than 1. So let's say that the beta is 0.88. What we're interested in is what is the required rate of return on Procter & Gamble. Well, because Procter & Gamble is less risky than the market, then we're not going to require a 6% premium. That's the average market premium. The risk premium in the market is 6%. That means the average stock of average risk is going to have a 6% 6% risk premium. But because this stock is less risky than the market, then we don't require an entire 6%. In fact, it's 5.28%. So we would invest in this particular asset if we thought we could get a 9.28% rate of return. All right. So that's what the capital asset pricing model could be used for, to help us determine the required rate of return on an asset given its risk. If we were looking at investing in an asset that had a beta of 1, we would expect to earn a 10% rate of return. We've said here an asset with a 0.88, we would require, it looks like 9.28. What if it had a beta of 0.8? Well, plug in 0.8 into the formula, and that's going to be 6 times 0.8 is 4.8. This would be 8.8. What if we were looking at investing in an asset that had a beta of 1.3? Well, we would want the required rate of return. We want 4% plus something to compensate us for the market risk. The market risk premium is 6, but because our stock that we're looking at, 1.3, is 30% riskier than the market, because the market has a beta of 1, so a beta of 1.3 is 30% more, then we want 1.3 times that, which is going to be 7.8. This is going to give us an 11.8% rate of return. So that's what the capital asset pricing model, well, among many things, but that's one of the things that it's useful for, to help us determine the required rate of return on an asset given its risk. All right, I'm going to stop there. I think you've got plenty of information to help you read and understand the chapter. I will focus primarily on what we've discussed in our chapters. So I hope this is useful and beneficial and understandable.